Right now, as you read this, 4 astronauts are flying through a region of space where the environment itself is actively trying to destroy their DNA. Not metaphorically, not as a distant statistical risk buried in a risk assessment document. Their cells are being struck right now by particles moving at a significant fraction of the speed of light. Particles with enough energy to snap both strands of the DNA double helix like a thread pulled too tight. Every hour of their mission, this is happening inside the bodies of Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. The mission is Artemis II. It launched on April 1st, 2026, making these 4 people the first humans to leave Earth's protective magnetic field since December 1972, when the crew of Apollo 17 splashed down in the Pacific and nobody went back. For 53 years, every human being who went to space stayed close enough to Earth that our planet's invisible magnetic shield, a bubble of deflected particles shaped by the molten iron churning at our planet's core, kept the worst of the universe's radiation from reaching them. Artemis II has left that bubble behind. What the crew is flying through right now and what it is doing to their bodies at the cellular level is the subject of this video. We are going to follow their flight path, zone by zone, layer by layer, and at each stage explain precisely what radiation environment they are entering, what it does to a human cell when it hits, and what NASA is doing to protect them, and where that protection runs out. Right now, without you doing anything, without any medical procedure or unusual exposure, your body is repairing damage to your DNA. Not occasionally, constantly. Every single day, between 10,000 and 100,000 individual lesions accumulate in your genetic code from background radiation, from the ultraviolet light that reaches your skin through a window, from the ordinary chemical reactions that keep your cells alive. Your body has been handling this since before you were born, and it handles it so efficiently that the vast majority of people will never experience any consequence from it whatsoever. The reason this works is that your DNA repair machinery is extraordinarily sophisticated. It patrols the genome continuously, identifies breaks and damaged bases, and fixes them with a precision that would be remarkable even in an engineered system. Most of the damage your cells sustain every day is repaired before it can cause any harm. The system is not perfect. Nothing biological is. But for the radiation levels most people encounter on Earth, it is more than adequate. Space radiation exploits the limits of that system in a specific and brutal way. When ionizing radiation strikes a DNA molecule, it can sever one or both of the 2 strands that make up the double helix. A single strand break, where only one side of the latter is cut, is manageable. Your cells have dedicated machinery for this. It happens thousands of times a day, and it is repaired quickly and accurately. The problem arises with what radiation biologists call a double-strand break, a point where both strands of the helix are severed at the same location simultaneously. The British Journal of Cancer has described this as the principal lesion that, if not adequately repaired, can lead to cell death through lethal chromosomal damage. When both sides of the latter are cut at the same point, the broken segment is no longer anchored to anything. It simply floats free inside the cell nucleus, and the cell must now find both ends and rejoin them correctly, without losing any of the genetic information that was encoded there. The cell has 2 main pathways for doing this. The first is called homologous recombination. It is slow, taking several hours, but it is accurate because it uses the sister copy of the damaged chromosome as a template to rebuild the broken section from scratch. Think of it as a master carpenter who, when a beam splinters, cuts a perfect replacement from an identical piece of timber and fits it precisely into place. The second pathway is called non-homologous end joining. It is fast, operating in minutes rather than hours, but it is error-prone because it simply captures the broken ends and ligates them back together without checking whether the join is genetically correct. This is more like someone nailing two broken pieces of wood back together and hoping the grain still matches. Non-homologous end joining is the dominant repair pathway in most human cells, which means that when your DNA breaks, the faster but sloppier repair system does most of the work. When non-homologous end joining makes an error in a gene that normally controls cell division, a gene that tells a cell when to grow and when to stop, the result is a cell that no longer receives that stop signal. It multiplies, and it keeps multiplying. That is the cellular origin of cancer, described at its most fundamental level. Now consider what makes space radiation different from the background radiation your cells handle every day. The difference is not simply quantity, it is geometry. Low-energy radiation, like X-rays, deposits its energy sparsely along the path it travels through tissue, creating isolated breaks that are spread far enough apart that the repair machinery can address them one at a time. High-energy heavy ion particles, the kind produced by galactic cosmic rays, are different in kind, not just degree. They deposit energy densely and continuously along a narrow track through tissue, creating what researchers call clustered DNA damage, multiple simultaneous double-strand breaks packed into a small region of the helix. The repair machinery was not designed to handle this. When several breaks occur within nanometers of each other, the ends from one break can be mistakenly joined to the ends from a neighboring break, creating chromosomal rearrangements that are far more difficult to correct and far more likely to produce cancerous mutations. In neurons, the cells of the brain, this problem is compounded by a fact that has no equivalent in most other tissues. Neurons do not divide and replace themselves. A liver cell or a skin cell that dies can be replaced by a neighboring cell dividing to fill the gap. A neuron that sustains damage it cannot repair either accumulates that damage permanently or dies outright, and in either case, it is not replaced. Charles Limoli and his team at the University of California, Irvine published research in 2016 using mice exposed to simulated galactic cosmic radiation, showing measurable impairments in spatial memory, executive function, and recognition memory that persisted for at least 24 weeks after a single exposure. The hippocampus, the brain structure most central to forming and storing new memories, showed significant reductions in the complexity of neuron structure in irradiated animals. These were not animals that received catastrophically high doses. They received doses within the range relevant to deep space missions. That is what ionizing radiation does inside a single cell. Now, consider that Artemis II is currently flying through 3 distinct radiation environments, each one producing those cellular events by a different mechanism, at a different rate, with a different level of predictability. The boundary between those environments is not marked by any visible feature of space. No color change, no turbulence, no signal inside the capsule. The crew moves through them the way a ship moves through water, feeling nothing while the damage accumulates invisibly around them. The first of those environments is one they encountered within minutes of launch. Let's look at Zone 1. The Van Allen Belts. In January 1958, the United States launched its first satellite into orbit, a small cylindrical instrument called Explorer-1, carrying a cosmic ray detector designed by a physicist named James Van Allen. The data that came back was immediately puzzling. At certain altitudes, the detector appeared to stop working entirely, registering nothing where it should have been registering particle counts. Van Allen looked at the numbers and reached a conclusion that no one had anticipated. The detector was not malfunctioning. It was being overwhelmed. The radiation levels at those altitudes were so far beyond what anyone had predicted that the instrument had simply saturated and gone silent. What Van Allen had found, and what he confirmed with a second satellite later that year, was a region of space surrounding Earth so thick with trapped charged particles that it registered as a blank on instruments designed to measure radiation. Those regions are now called the Van Allen radiation belts, and they are the first environment that Artemis II had to cross on the way to the moon. The belts exist because of Earth's magnetic field. The same invisible structure that makes a compass needle point north also acts as an enormous trap for charged particles arriving from the sun and from deeper space. Instead of passing through and continuing on their way, these particles become caught in the magnetic field lines, spiraling back and forth between the planet's north and south magnetic poles in trajectories that can last for years. Over time, magnetic interactions accelerate them to higher and higher energies, and they accumulate in two distinct zones. The inner belt occupies the region between roughly 1,000 and 12,000 kilometers above Earth's surface. It is dominated by high-energy protons, hydrogen nuclei stripped of their electrons and accelerated to velocities that carry significant biological punch. These are not gentle particles. They are energetic enough to penetrate the walls of a spacecraft and deliver ionizing radiation directly to the tissue of anyone inside. The outer belt, extending from roughly 15,000 to 25,000 kilometers, is composed primarily of electrons. Electrons are less massive and less penetrating than protons, but they interact with spacecraft materials in ways that generate secondary radiation, and prolonged exposure to the outer belt carries its own biological costs. Every mission to the moon passes through both belts on the way out and both belts again on the way back. There is no route that avoids them entirely. The geometry of Earth's magnetic field means that any spacecraft climbing from low Earth orbit toward the moon must transit through both zones, and any spacecraft returning must do the same. What NASA can control is not whether the crew passes through the belts, but how. The trajectory that minimizes time in the most intense regions and the orientation of the spacecraft during that transit. The data that informed those decisions for Artemis II came from the uncrewed Artemis I mission in 2022, which carried more than 5,600 radiation sensors distributed throughout the capsule and embedded in two life-sized mannequins. When Thomas Berger and his team at the German Aerospace Center analyzed those measurements and published the results in Nature in September 2024, one finding stood out with particular clarity. The radiation environment inside Orion during the Van Allen belt transit varied by a factor of 4, depending on where in the capsule the measurement was taken. The seat nearest the least shielded wall received 4 times the dose of the seat nearest the most protected section, and both were inside the same spacecraft. A second finding was even more operationally significant. When Orion rotated 90 degrees during the transit of the inner proton belt, turning so that the spacecraft's most heavily shielded face pointed toward the incoming radiation, the dose rates inside the capsule dropped by approximately 50%. The protons in the inner belt do not arrive from every direction equally. They stream along magnetic field lines in a preferential orientation and presenting the densest part of the spacecraft's structure toward that stream cuts the exposure in half. That maneuver is now a planned and confirmed element of the Artemis II mission profile. Even with the optimized trajectory and the rotation maneuver, the Van Allen belt transit remains the single highest dose rate event of the entire mission. The dose rates the crew experiences during that roughly 60-minute crossing are comparable to what a large solar particle event would deliver, concentrated into 1 hour rather than spread across a day. It is the sharpest radiation spike of the journey, and it happens before they have even left Earth's neighborhood. Once Orion climbs out of the outer belt and beyond approximately 60,000 kilometers, the familiar geography of Earth's magnetic protection falls away entirely. The crew enters what space radiation scientists call the interplanetary environment, where a fundamentally different category of threat takes over, one that has been traveling toward them for millions of years and cannot be turned away by any maneuver or material that engineering has yet devised. Zone 2. Galactic Cosmic Rays. The name is misleading, and it is worth correcting before going any further. Galactic cosmic rays are not rays in any conventional sense of the word. They are not beams of light or waves of electromagnetic energy. They are particles, physical objects with mass, charge, and momentum that have been traveling through the galaxy for millions of years before arriving, at this particular moment, at the hull of a spacecraft carrying 4 human beings. Most of them are protons, the same particles that make up the nucleus of a hydrogen atom. Others are helium nuclei or the stripped nuclei of heavier elements, iron, silicon, oxygen, carbon, from which all electrons have been torn away by the violent processes that launch them into space. Those processes include supernovae, the explosive deaths of massive stars that release more energy in a few seconds than our sun will produce across its entire 10 billion year lifetime, as well as the extreme magnetic environment surrounding black holes and neutron stars. The particles, accelerated by these events, have been gaining speed ever since, and by the time the most energetic of them reach the outer edge of our solar system, they are moving at velocities that approach the speed of light. This is the environment that no spacecraft wall can stop. When a high-energy galactic cosmic ray particle strikes the aluminum hull of Orion, it does not simply slow down and stop. It shatters both the incoming particle and the target nucleus fragment into a spray of secondary particles, neutrons, gamma rays, lighter ions, that continue inward through the spacecraft. This process is called nuclear spallation, and its consequence is deeply counterintuitive. Beyond a certain thickness of shielding material, adding more mass does not reduce the biological dose reaching the crew. It increases it because a thicker wall produces a larger and more complex secondary particle shower. NASA's own published research states plainly that passive shielding is ineffective in protecting crew members from the biological impacts of fast-moving, highly charged galactic cosmic radiation nuclei. The spacecraft's walls cannot be made thick enough to solve this problem without making them so thick that they create a worse problem. Galactic cosmic rays also arrive from every direction simultaneously. Unlike solar radiation, which streams outward from one source, galactic cosmic rays are isotropic. They come from above and below, from the front and the back, from every angle at once. No orientation maneuver can present a more shielded face toward them because they have no preferential direction. No trajectory choice can reduce exposure to them because they fill interplanetary space uniformly. No shelter protocol can block them because no practical thickness of passive shielding stops the most energetic particles. For the Artemis II crew, galactic cosmic ray exposure during their 10-day mission is simply the baseline cost of being in interplanetary space, a constant, inescapable background that accumulates whether they are asleep or working, whether the sun is active or quiet. The biological consequences of this are most serious for a specific class of particles called HZs, high charge as high energy nuclei, particularly iron 56. Because iron nuclei are large and heavily charged, they interact intensely with the matter they pass through, depositing energy densely and continuously along a narrow track through tissue. In Section 2, we described how clustered DNA damage, multiple simultaneous double-strand breaks packed into a small region of the helix, is the kind of damage that repair machinery struggles to handle correctly. An iron nucleus passing through a cell does not produce one isolated break. It leaves a dense trail of ionization damage along its entire path, creating exactly the kind of clustered, complex injury that is most likely to be repaired incorrectly or not repaired at all. When that track passes through a neuron, the consequences are compounded by the same biological fact established earlier. Neurons do not replace themselves, and Charles Limoli and his team at the University of California, Irvine, measured what happens when you expose the brains of living mice to simulated galactic cosmic radiation at doses relevant to a deep space mission. Their results, published in scientific reports in 2016, documented significant and persistent impairments in spatial memory, recognition memory, episodic memory, and executive function, all still measurable at 24 weeks after a single exposure, more than 6 months after the radiation event itself. Limoli described the findings as revealing an unexpected sensitivity of the central nervous system to cosmic radiation. Unexpected because the doses involved were not dramatically higher than those anticipated on actual missions. Francis Cucinotta, one of the leading researchers in space radiation risk modeling, applied findings like these to actual mission scenarios and produced a statistical prediction that approximately 1 in every 2.8 astronauts on a deep space mission would experience some level of memory impairment attributable to radiation exposure. That prediction carries significant uncertainty. Rodent models are imperfect proxies for human cognition, and laboratory irradiation conditions do not perfectly replicate the chronic low-dose experience of actual spaceflight. For a 10-day lunar mission specifically, the accumulated galactic cosmic ray dose is far below what a Mars transit would deliver, and cognitive effects are not an anticipated concern for the Artemis II crew. But the finding establishes something that cannot be set aside. The human brain is more vulnerable to this category of radiation than the scientific community previously assumed, and that vulnerability does not disappear simply because a mission is short. Galactic cosmic rays are the tax that cannot be avoided, the unavoidable baseline that comes with leaving Earth's magnetic field. But superimposed on that baseline is a threat that is more intense, more sudden, and in some ways more dangerous precisely because it is unpredictable. It is a threat that already came within a few months of killing a crew of Apollo astronauts who were not there to be killed, and one that Artemis II is flying through during the most active period of the Sun's 11-year cycle. Scientists call it a solar particle event, and the timing of one relative to an astronaut's location in space can be the difference between a manageable exposure and a medical emergency. Zone 3. Solar particle events. In August 1972, one of the largest solar storms of the 20th century erupted from the surface of the Sun and sent a wave of energetic particles racing through the inner solar system. It was not a gentle event. Radiation physicists who have modeled the exposure an unprotected astronaut would have received in deep space during that storm estimate a dose of several grays, a unit of absorbed radiation energy that, at those levels, produces what medicine calls acute radiation syndrome. The sequence is predictable and grim: nausea and vomiting within hours, followed over the next several days by the progressive failure of blood cell production as radiation systematically destroys the bone marrow that generates them. For a crew in deep space, with no hospital and no means of emergency return, the outcome at that dose would not have been survivable. By extraordinary luck, no one was there. Apollo 16 had splashed down in April. Apollo 17 would not launch until December. The storm moved through empty space, and the only people who knew how close it had come were the radiation physicists who ran the numbers afterward. That August 1972 event is now the reference scenario that NASA uses when designing radiation protection for every deep space mission. The worst case that the system must be capable of handling. The Sun that Artemis II is flying near right now is an active sun. We are currently near solar maximum, the peak of the approximately 11-year cycle of magnetic activity that governs how often and how violently the Sun erupts. During solar maximum, the Sun's magnetic field is more tangled, more stressed, and more prone to releasing that stored energy in the form of solar flares and coronal mass ejections. A solar flare, the most energetic category of eruption in the solar system, can release more energy than 1 billion hydrogen bombs within a span of minutes. The electromagnetic radiation it produces, including X-rays and gamma rays, travels at the speed of light and reaches Earth in roughly 8 minutes. The charged particles it accelerates, mostly protons, driven to significant fractions of light speed by the magnetic shock waves of the eruption, arrive later, anywhere from 20 minutes to several hours after the initial flash, depending on the event's geometry and the particle energies involved. That delay is both the danger and the opportunity. It is the danger because the arrival of a large solar particle event can escalate from background levels to potentially harmful dose rates within an hour. It is the opportunity because it provides a window, however narrow, for a monitoring system to detect the warning signs and give the crew time to respond. For Artemis II, NASA has assembled the most comprehensive solar surveillance network ever organized for a crewed mission. The Space Radiation Analysis Group at Johnson Space Center and the Moon to Mars Space Weather Analysis Office at Goddard monitor the Sun continuously around the clock. NOAA's Space Weather Prediction Center contributes additional forecasting, and a new spacecraft called Solar One, positioned at the L1 Lagrange point, approximately 1.5 million kilometers toward the Sun, provides real-time particle and magnetic field measurements from a location where it can detect eruptions before their effects reach the crew. The Perseverance rover on Mars, currently on the far side of the Sun relative to Earth, is contributing observations of solar activity from a vantage point that ground-based observatories cannot match. The University of Michigan engineering team has developed a solar particle forecasting model that the Space Radiation Analysis Group is actively monitoring throughout the mission. The model ingests continuous imagery from the Solar Dynamics Observatory and the Solar and Heliospheric Observatory tracking the magnetic evolution of the sun's surface in real time and assessing the probability of a significant eruption up to 24 hours in advance. When Lori Glaze of NASA spoke to reporters in late March, she described the current solar forecast as clear. No active regions of concern on the sun's visible face at that moment. But the mission spans 10 days, and the sun operates on its own schedule. If an alert is issued, the crew has 30 minutes to construct a radiation shelter inside Orion by repositioning stowage bags, packed with water, food, and equipment, along the walls of the capsule's most heavily shielded section, near the heat shield and service module where the densest mass sits. Inside that improvised shelter, even the worst solar particle event that modeling considers plausible would be kept below 150 millisieverts, a level at which no acute radiation effects occur. The system works. The question is always whether the warning comes in time and whether the sun cooperates. Hazel Bain, a research scientist at NOAA's Space Weather Prediction Center, has noted that the fundamental challenge of solar forecasting has not changed since the Apollo era. The physics of what the sun can do is the same. What has changed is the quality of observations and the sophistication of the models. The analogy NASA itself uses is weather forecasting in the 1950s. The science exists, the tools are improving, and the predictions are getting better. But certainty remains out of reach, and the sun can change in hours. 3 radiation environments, 3 different physics, 3 different levels of predictability. What links them is the same spacecraft, the same 4 crew members, and the same fundamental question that every section of this video has been building toward: what exactly is NASA doing to manage all 3 threats simultaneously? And where does that management run out? Let's look at the Orion spacecraft. How the shielding works. Radiation protection was not added to Orion late in the design process as a precaution. It was built into the architecture of the spacecraft from the beginning, shaping decisions about structure, materials, and interior layout that might otherwise appear to be purely practical choices about storage and weight distribution. The capsule's outer walls are aluminum alloy, a material chosen for structural strength and thermal performance, not primarily for radiation shielding. Aluminum alone provides only modest protection against the particle environments Artemis II is flying through. What makes Orion more capable than its material composition suggests is the deliberate arrangement of mass inside the capsule. Water tanks, food storage containers, and equipment lockers are not positioned randomly according to convenience. They are placed along the outer walls of the crew module in configurations that add dense mass between the crew and incoming radiation. Every kilogram of stored supplies serves a dual purpose. It sustains the crew on the journey, and it absorbs energy from particles that would otherwise reach them unimpeded. Jessica Voss, NASA's Deputy Health and Medical Technical Authority for Orion, has described this principle as using the spacecraft's own necessary payload as part of its radiation defense, turning the practical requirements of a 10-day mission into shielding material. The monitoring system layered on top of this passive architecture is the most sophisticated ever flown on a human deep space mission. At its center is the Hybrid Electronic Radiation Assessor, known as HERA, a network of 6 radiation detector chips developed through a collaboration between NASA and CERN's MEDIPICS research program, the same scientific effort that produced particle detection technology for the Large Hadron Collider. These chips are distributed at different locations throughout the crew cabin, and they do not simply measure total radiation dose. They identify the type of particle arriving, whether proton, electron, or heavy ion, and measure its energy in real time. That distinction matters because different particle types carry different biological risks and require different responses. The data streams continuously to the Space Radiation Analysis Group at Johnson Space Center, where it is monitored alongside the solar weather forecasts that track what might be coming from the sun. Each of the 4 crew members also carries a personal crew active dosimeter worn directly on the body, transmitting their individual accumulated dose back to Earth throughout the mission. The dosimeters and the Hera sensors operate on a threshold system. When dose rates inside the capsule cross the first defined level, monitoring intensity increases and medical teams are notified. When they cross the second, higher threshold, the crew receives a recommendation to move to the shelter position. The final layer of the system is the AstroRad vest, developed by the Israeli company STEMRAD under the leadership of Dr. Oren Milstein, and validated during Artemis I using the Helga and Zohar mannequins. The vest is constructed from hydrocarbon polymers, materials with an exceptionally high concentration of hydrogen atoms. Hydrogen is the most effective element for stopping protons, and solar particle events are predominantly proton events, which means the vest targets the specific threat it was designed for. Data from Artemis I showed that the vest reduced radiation dose to the most sensitive internal organs, bone marrow, lung tissue, and breast tissue, by between 40 and 60% during simulated solar storm conditions. Taken together, these layers form a defense-in-depth system. No single component needs to be perfect because each one covers the gaps that the others leave. Based on Artemis I measurements, NASA's confidence is that even during a large solar particle event, doses inside the shelter will remain below 150 millisieverts, a level at which no acute radiation effects occur in humans. The engineering is genuinely impressive, a system built from hard lessons, real data, and decades of radiation biology research. But every system has limits, and understanding those limits requires confronting an uncomfortable truth at the heart of deep space radiation physics. One category of threat passes through all of this protection without slowing down, not through gaps in the design, not because of engineering failures, through the physics of what these particles are. To understand where Orion's protection runs out, it helps to understand what shielding actually does at the physical level. When a charged particle enters a material, aluminum, plastic, water, anything with mass, it interacts with the electrons and atomic nuclei of that material, losing energy through those interactions until it slows down and stops. The denser and thicker the material, the more interactions occur and the more energy the particle loses before it reaches the other side. This is why the AstroRad vest works against solar protons, and why the shelter's repositioned stowage bags provide meaningful protection during a solar storm. Solar energetic particles are energetic, but they are not so energetic that sufficient mass cannot stop them. The physics of conventional shielding is well matched to the threat they represent. Galactic, cosmic ray particles operate in a different energy regime entirely. The iron 56 nuclei that carry the highest biological risk arrive with energies measured in giga-electron volts, a unit that reflects kinetic energy so large that the particle has been accelerated to a velocity close to the speed of light. When a particle at this energy level strikes an atomic nucleus in a spacecraft's aluminum hull, it does not simply slow down and stop. It shatters both the incoming particle and the target nucleus fragment into a spray of secondary particles, neutrons, gamma rays, lighter ions, that continue inward through the spacecraft. This process is called nuclear spallation, and its consequence is deeply counterintuitive. Beyond a certain thickness of shielding material, adding more mass does not reduce the biological dose reaching the crew. It increases it because a thicker wall produces a larger and more complex secondary particle shower. NASA's own published research states plainly that passive shielding is ineffective in protecting crew members from the biological impacts of fast-moving, highly charged galactic cosmic radiation nuclei. The spacecraft's walls cannot be made thick enough to solve this problem without making them so thick that they create a worse problem. What Orion's aluminum structure does accomplish, and this matters, is a meaningful reduction from the galactic cosmic ray levels that would reach an unprotected person in open space. Data from the Artemis I mission, published in Nature in 2024 by a team led by researchers at the German Aerospace Center, showed that cosmic ray dose equivalent rates inside Orion were approximately 60% lower than measurements taken by less shielded spacecraft in similar environments. That reduction is real and significant. It simply cannot be extended further without crossing into the counterproductive territory where spallation overwhelms the benefit of additional mass. The practical result for the Artemis II crew is that their 10-day galactic cosmic ray exposure will be roughly equivalent to 1 month aboard the International Space Station, despite the mission lasting only 10 days, because ISS astronauts retain partial shielding from Earth's magnetic field that Artemis II leaves behind entirely. When that dose is combined with the Van Allen belt transit and the background solar radiation of the mission, the total accumulated exposure is expected to represent approximately 5% of NASA's career dose limit of 600 millisieverts. That career limit was established to correspond to a 3% increase in cancer mortality risk above baseline for a 35-year-old female astronaut. The most radiation-sensitive demographic in NASA's crew population, and therefore the standard against which all mission planning is measured. For a single 10-day mission, 5% of a career limit is a number that NASA's bioengineer Janet Barzilla and radiation risk modeler Xiaowen Hu describe as well within acceptable bounds. The concern is not Artemis II in isolation. It is what Artemis II represents as the first step in a program that intends to put people on the lunar surface for weeks at a time, and eventually send them on a 6-month transit to Mars, where galactic cosmic ray exposure alone could consume the majority of that career limit in a single journey, with no solution to the spallation problem yet in hand. The gap between what shielding can do and what galactic cosmic rays can do is the defining unsolved problem of deep space human exploration. But there is a second gap, one that is less visible and, in many ways, more personal, in how radiation risk is calculated and whether those calculations fully account for the organ most susceptible to permanent, irreversible damage. The one that does not grow back, the one where radiation biology gets its most unsettling and least resolved results. The brain problem, what nobody fully understands yet. Cancer risk from radiation exposure is frightening, but it is at least a problem that science knows how to model. Decades of research on radiation workers, medical patients, and the survivors of nuclear events have produced statistical frameworks that translate dose into probability with reasonable confidence. The brain presents a different and less tractable problem, and it is the one that space radiation biologists describe with the most careful language, not because they are trying to alarm anyone, but because the honest answer to the question of what deep space radiation does to human cognition is that the science is still being written. The reason the brain is different begins with the same biological fact introduced earlier in this video. Neurons do not divide and replace themselves. A liver cell that sustains irreparable radiation damage can be replaced by a neighboring cell dividing to fill the gap. A neuron cannot. It either repairs itself, accumulates the damage permanently, or dies. And in any of those outcomes, what is lost is not recovered. For tissues that turn over continuously, radiation damage is a problem of probability spread across a large and constantly renewing population of cells. For the brain, damage is cumulative and permanent in a way that no other tissue quite matches. When a high-energy, heavy ion particle passes through brain tissue, it leaves behind the dense ionization tract described earlier, a narrow corridor of intense damage running through whatever cellular structures happen to lie in its path. In neurons, the structures most vulnerable to this kind of disruption are synapses, the junctions through which one neuron communicates with another, and dendrites, the branching extensions through which neurons receive those signals. Charles Limoli's laboratory at the University of California, Irvine has documented across multiple rodent studies that even doses well below those anticipated on a Mars mission cause measurable reductions in dendritic complexity and synaptic spine density, the physical architecture through which neural networks process and store information. The damage is not hypothetical. It is visible under a microscope in tissue taken from irradiated animals. The behavioral consequences of that structural damage were quantified in a 2016 paper published in Scientific Reports. He titled Cosmic Radiation Exposure and Persistent Cognitive Dysfunction. Rodents irradiated with simulated galactic cosmic radiation showed measurable deficits across 6 independent behavioral tests: spatial memory, episodic memory, recognition memory, executive function, fear extinction, and anxiety, at both 12 and 24 weeks after exposure. More than 6 months after a single radiation event, the impairments were still present. Limoli described the findings as revealing an unexpected sensitivity of the central nervous system to cosmic radiation. Unexpected because the doses that produced these effects were not dramatically higher than those relevant to real missions. Francis Cucinotta applied findings like these to human mission scenarios and produced a statistical prediction that approximately 1 in every 2.8 astronauts on a deep space mission would experience some level of memory impairment, and 1 in every 5.1 would experience anxiety-like behavioral changes attributable to radiation exposure. Those numbers demand honest context. Rodent cognition is not human cognition. Laboratory irradiation, delivered acutely in a single session, does not perfectly replicate the chronic low-dose rate exposure of an actual mission. A 2025 study led by Sang-Hee Yoon at the Children's Hospital of Philadelphia, using a more realistic simulation of 33 different ion beams rather than a simplified single-beam exposure, found cognitive impairments that were measurably less severe than those reported in earlier acute irradiation studies. The research community takes this as a signal that some earlier predictions may have overstated the risk, though none of the researchers involved would describe the risk as negligible. What the accumulated science establishes is specific. The brain's vulnerability to deep space radiation is real. It is non-zero, and it is still being quantified with each successive study. For the Artemis II crew, the 10-day galactic cosmic ray dose is small enough that cognitive effects are not an anticipated concern for this mission. But the crew is simultaneously serving as research subjects for the missions that follow. They are providing saliva samples at multiple points during the flight to track immune biomarkers. Before launch, their blood was used to create miniature laboratory models of their own bone marrow, biological analogs that NASA's research teams are studying in parallel with the mission, measuring in real time how radiation affects the specific tissue that produces blood cells. The data they generate in orbit will inform the risk models used to plan every subsequent deep space mission. The crew is not just flying through radiation. They are generating the data that will tell us whether the people who follow them to Mars can do so safely. But to understand what that data will actually show when Artemis II returns, we need to talk about the numbers themselves, not as abstractions, but as what they actually represent for 4 real people who accepted them with open eyes. Let's talk about the numbers. What 5% of a career limit actually means. NASA's career effective dose limit for astronauts is 600 millisieverts. That number did not come from an engineering convenience or a round number compromise. It came from a 2021 review by the National Academies of Sciences that concluded 600 millisieverts corresponded to a 3% increase in the risk of fatal cancer above baseline for the most radiation-sensitive demographic in NASA's crew population, a 35-year-old female astronaut. 3% is the threshold that the National Academies determined represented an acceptable occupational risk for a career in spaceflight, comparable to the elevated risks accepted by workers in other hazardous professions. The limit is not a line below which radiation causes no harm, and it is a line below which the additional risk is considered proportionate to the value of the work. The Artemis II mission is expected to deliver approximately 30 millisieverts to the crew over 10 days, roughly 5% of that career limit consumed in a single mission. To place 30 millisieverts in everyday terms, the average American accumulates approximately 3 millisieverts per year from all background sources combined: natural radioactivity in soil and building materials, cosmic radiation at ground level, medical imaging, and the small amount of radioactive material present in food and water. 10 days on Artemis II delivers roughly 10 times what most people receive across an entire year on Earth, compressed into less than a fortnight. Stated that way, the number sounds significant. In the context of NASA's safety framework, it is manageable for this mission. The concern is not Artemis II. The concern is what Artemis II represents as the first data point in a trajectory that extends toward the lunar surface and eventually toward Mars. A 6-month transit to Mars, depending on where the mission falls within the solar cycle and how much shielding the spacecraft carries, has been estimated to deliver between 300 and 500 millisieverts, between 50 and 80% of an astronaut's entire career limit in a single outbound journey, before the return trip, before any time on the Martian surface, and before any previous missions are accounted for. The sensors flying on Artemis II, 6 Hera detectors distributed through the cabin, 4 personal dosimeters worn by the crew, are not measuring exposure for its own sake. They are validating the predictive models that will determine whether crewed Mars missions are biologically feasible within the current regulatory framework. Janet Barzilla, a bioengineer at Leidos who has worked with NASA's Johnson Space Center on radiation risk assessment, told Scientific American she expects the Artemis II measurements to align closely with what Artemis I established. If they do, the models are confirmed. If they diverge, every projection built on those models requires revision. There is one further complication that the numbers alone do not capture. Galactic cosmic rays are assigned what radiation physicists call a quality factor, a multiplier applied to their absorbed dose to account for the fact that heavy ions cause more biological damage per unit of energy than X-rays do. That quality factor, however, was derived primarily from high-dose laboratory experiments rather than from the chronic low-dose exposures that characterize actual spaceflight. Whether it accurately reflects the biological impact of years of background galactic cosmic ray exposure at mission-relevant dose rates remains, as of today, an open and actively researched question. The numbers tell part of the story. The mission data will fill in the rest. But behind every number, behind every millisievert and quality factor and career limit percentage, there are 4 specific people who looked at these calculations and said, yes. Understanding who they are and what they agreed to is the dimension of this story that the physics alone cannot carry. Everything discussed in this video, the double-strand breaks, the secondary particle cascades, the career limit calculations, the cognitive risk models, is happening right now inside the bodies of 4 specific people. It is worth knowing who they are. Reid Wiseman is the mission commander, a former Navy test pilot who logged 167 days aboard the International Space Station before being selected to lead the first crewed deep space mission in over half a century. He is the person responsible for the crew's safety in an environment where the hazards are invisible, cumulative, and cannot be outrun. Every threshold the Orion dosimeters track, every shelter protocol the crew has rehearsed, every solar forecast being monitored at Johnson Space Center. These are ultimately in service of the 4 people he is responsible for bringing home. Victor Glover is the mission pilot, a Navy commander and fighter pilot who flew to the International Space Station aboard SpaceX's Crew Dragon for a 6-month expedition. On the first day of this mission, Glover became the first person of African descent to travel beyond low Earth orbit, a boundary that human spaceflight had maintained for 65 years without crossing. His place in that history is not yet finished being written. Christina Koch is a mission specialist who holds the record for the longest continuous spaceflight by a woman, 328 days on the International Space Station during a previous mission. On this mission, she became the first woman in history to travel beyond low Earth orbit, crossing a threshold that the entire preceding arc of human spaceflight had not crossed in 65 years of trying. Jeremy Hansen is a Royal Canadian Air Force fighter pilot and Canadian Space Agency astronaut who became, on the first day of Artemis II, the first non-American citizen to travel beyond low Earth orbit. He has described the mission as a threshold, not just for himself, but for the proposition that deep space exploration belongs to more than one nation. All 4 of them agreed before launch to serve as research subjects alongside their roles as crew. They wear wristbands tracking their sleep and movement. They submitted blood before the mission so that bone marrow analogs, miniature laboratory models of their own marrow, could be created and studied on Earth in parallel with their flight. They will provide saliva samples at multiple points during and after the mission to track how their immune systems respond to radiation and the stress of deep space. The radiation they are absorbing over these 10 days will follow them for the rest of their lives. NASA estimates the additional cancer mortality risk from a 30 millisievert dose at less than 1% above baseline. That is a small number. It is not zero. These 4 people know exactly what it means, and they chose to accept it, so that the people who follow them will face the same environment with better data, better models, and better protection than exists today. 4 people, 4 bodies, 4 sets of DNA-absorbing radiation in interplanetary space for 10 days, and when they return, when Orion splashes down in the Pacific and the crew steps aboard the recovery ship, the science does not end there. What they carry back from this mission extends far beyond the data on the hard drives. Let's see what happens after they land. When Orion splashes down in the Pacific and the Artemis II crew boards the recovery ship, the radiation exposure they accumulated over 10 days does not end with the mission. It becomes part of their biology in a way that will take years, and in some cases decades, to fully reveal itself. Radiation-induced cancer does not announce itself in the weeks after exposure. The mechanism is slow by design. A mutation occurs in a single cell. That cell divides and passes the mutation to its daughters, and those daughters divide again, accumulating further errors over years until the population of mutated cells grows large enough to become a detectable tumor. The latency period between radiation exposure and a clinically apparent cancer is typically measured in years for leukemia and in decades for solid tumors. The health consequences of what Wiseman, Glover, Koch, and Hansen are absorbing right now will not be fully visible for a long time after they return. NASA's long-term astronaut health tracking program is designed to capture exactly this delayed picture. The Artemis II crew will receive regular medical evaluations for the rest of their lives, generating longitudinal health data that researchers can compare against the predictions made by radiation risk models. Every health outcome, every cancer diagnosis, every cardiovascular event, every cognitive change feeds back into the models that will govern the planning of future missions. The crew's bodies, over the decades that follow this flight, are as much a scientific instrument as any sensor aboard Orion. The biological monitoring that began before launch continues after landing. The saliva samples collected during the mission to track immune biomarkers will be compared against post-flight samples taken in the weeks and months following return, allowing researchers to measure how the immune system recovers from the combined stresses of radiation, isolation, and the distance from Earth that characterizes deep space. One specific concern that researchers will be watching for is viral reactivation, the tendency of latent viruses like the varicella-zoster virus, responsible for chickenpox and shingles, to become active again during spaceflight. This phenomenon has been documented repeatedly on the International Space Station, and scientists want to know whether the deeper radiation environment of a lunar trajectory amplifies it. The Avatar experiment, organ-on-a-chip devices flying on Artemis II for the first time, beyond the Van Allen belts, will provide a layer of biological detail that no previous deep space mission has generated. These devices contain human cells arranged to mimic the functional behavior of specific organs, and they can detect changes in cellular function that a standard blood test would miss entirely. Rihanna Bokhari at the Translational Research Institute for Space Health at Baylor College of Medicine has described this kind of tissue-level monitoring as essential for understanding radiation effects that operate below the threshold of clinical symptoms, the quiet, accumulated damage that precedes any observable health event by years. Artemis II is not the end of this story. It is, by NASA's own description, the first crude step in a program that intends to put people on the moon's surface, build a lunar base, and eventually send humans to Mars. Each of those steps reaches further into the radiation environment, and that means the lessons of Artemis II are not just about this crew. They are about whether any of what comes next is biologically possible. That question has a specific answer, or at least the beginning of one, and it requires confronting the hardest version of the problem. Let's talk about what Artemis II means for Mars. A 10-day flight around the moon and back is, in radiation terms, a manageable problem. The doses are real, the risks are non-zero, and the science of measuring and mitigating them is genuinely complex. But the numbers remain within a framework that NASA's safety standards can accommodate. Mars is a different category of problem entirely, and it is the reason that every sensor on Artemis II, every dosimeter reading, and every biological sample collected during this mission carries implications that extend decades beyond the current flight. A crude Mars transit would take approximately 6 months in each direction. At the galactic cosmic ray flux levels relevant to the current solar cycle, that 6-month outbound journey would deliver between 300 and 500 millisieverts of radiation to the crew, between 50 and 80% of NASA's entire career dose limit consumed before the crew reaches the Martian surface, before any time is spent on the ground, and before the return journey begins. An astronaut who completed a round-trip Mars mission under current radiation conditions would, in most scenarios, exhaust their career radiation allowance entirely in a single flight. If they had flown any previous missions on the International Space Station on an Artemis lunar landing, they would almost certainly exceed it. The shielding solution that works for solar particle events does not translate to this problem. As established earlier, a passive shielding against galactic cosmic rays reaches a physical limit beyond which adding more mass produces more secondary radiation rather than less. Azita Valinia, an astrophysicist and former chief scientist at NASA's Engineering and Safety Center, has been direct about the constraint. The spacecraft walls can be optimized, but they cannot be made thick enough to reduce galactic cosmic ray dose to the levels that a multi-mission career framework requires, without triggering the spallation cascades that would make the interior of the spacecraft more hazardous than the space outside it. 3 research directions are currently being pursued in parallel. The first is pharmacological, developing compounds that reduce radiation sensitivity or accelerate DNA repair in exposed cells. A study published in the Journal of Neurochemistry in 2025, led by Sang-Hee Yoon at the Children's Hospital of Philadelphia, found that a dietary supplement called CDD-OEA partially mitigated the cognitive impairments observed in female mice exposed to simulated galactic cosmic radiation. The effect was real and measurable, and the researchers noted it as a promising avenue for further investigation. Clinical readiness for human spaceflight remains distant, but the direction is established. The second is active shielding, generating magnetic or electric fields around a spacecraft to deflect charged particles before they reach the hull, replicating on a small scale the function that Earth's magnetosphere performs for the entire planet. No practical active shielding system for a crewed spacecraft exists today, and the engineering challenges involved are substantial enough that no near-term solution is anticipated. The third is biological, identifying whether particular genetic variants confer measurably greater resistance to radiation damage and whether safe medical interventions could provide targeted protection to the tissues most vulnerable to galactic cosmic ray exposure. This line of research is the least mature of the three, but it is being pursued at multiple NASA-funded institutions as part of the broader program to make long-duration deep space missions survivable within acceptable risk thresholds. None of these approaches will be tested on Artemis II. What Artemis II will do is generate the baseline data from 6 cabin radiation sensors, 4 personal dosimeters, organ-on-a-chip tissue analogs, bone marrow models, and immune biomarker samples, that every subsequent decision about Mars mission feasibility will be built upon. The models that predict what a 6-month Mars transit will do to a human body are only as reliable as the measurements used to validate them. Artemis II is producing those measurements right now, which brings us back to right now, to what is happening at this exact moment inside Orion. While you have been watching this video, the Artemis II crew has been in space. As of today, April 2nd, 2026, Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen have completed their proximity operations demonstration, a carefully choreographed test of Orion's ability to maneuver manually relative to the interim cryogenic propulsion stage that carried them into high Earth orbit. Ground teams are now preparing the perigee rays burn that will reshape Orion's orbit in advance of the translunar injection. The engine firing that will release the crew from Earth's gravitational sphere of influence entirely and commit them to the trajectory that ends at the moon. The radiation monitoring systems have been active since the moment of launch. Inside Orion, right now, the 6 HERA sensors developed with CERN's Medipix collaboration are measuring the composition and energy of every significant particle that enters the cabin, transmitting that data continuously to the Space Radiation Analysis Group at Johnson Space Center. The scientists watching those numbers on the ground are seeing the same radiation environment the crew is experiencing in real time. The same galactic cosmic ray background, the same residual effects of the Van Allen belt crossing, the same solar flux that the University of Michigan forecasting model and NOAA's Space Weather Network are tracking for any sign of the eruptions that could change the mission's radiation picture within hours. Later this week, when the translunar injection burn sends the crew beyond Earth's magnetic field entirely, and Orion will begin its transit through the Van Allen belts on the outbound leg of the journey. The trajectory has been calculated to thread through the weakest regions of the belts. The 90-degree rotation maneuver that Artemis I data showed can cut inner belt proton exposure in half, is planned and ready. The shelter protocols are rehearsed. The dosimeters are active. Every system that this video has described is currently operational aboard a spacecraft carrying 4 people who are, at this moment, the only humans beyond the protection of Earth's magnetic field. The first to be in that position since the crew of Apollo 17 returned in December 1972. The radiation they are absorbing is being measured, logged, and transmitted. The science is happening right now in real time while you watch. What they are doing takes courage of a specific and unusual kind. Not the courage of the moment, but the courage of accepting an invisible, delayed risk for a purpose that extends far beyond themselves. That is the final dimension of Artemis II's radiation story, and it deserves the honest conclusion it has earned. The radiation environment of deep space is real, it is measurable, and it is genuinely hazardous. Not in the way that risk is sometimes described to make a bureaucratic point, not as a line item in a safety assessment document that exists to satisfy a regulatory requirement. Real, in the sense that photons and particles are physically breaking chemical bonds in living tissue right now, damaging DNA in ways that may not manifest as disease for years, and affecting the most sophisticated biological structure in the known universe, the human brain, in ways that science is still actively characterizing, in laboratories, in peer-reviewed journals, and on missions exactly like this one. That is the honest starting point. It would be dishonest to soften it, and it would also be dishonest to stop there. Artemis II is not an unprotected gamble. It is the most carefully measured, most thoroughly modeled, and most extensively instrumented, crewed mission to deep space in the history of human spaceflight. The 5,600 sensors that flew on Artemis I produced data that has been analyzed, published, and applied directly to the planning of this mission. The maneuver that cuts Van Allen belt proton exposure in half by rotating the spacecraft 90 degrees is not a contingency. It is a planned element of the flight profile, derived from real measurements taken on a real mission. The shelter that keeps solar storm doses below the threshold for acute radiation effects has been rehearsed by this crew. The career dose limit framework that defines what level of long-term risk is acceptable for a human being in this profession is in place. Are days, and for a 10-day mission delivering approximately 30 millisieverts, it will not be approached. What this mission cannot do is eliminate the risk. The galactic cosmic rays passing through Orion's walls right now cannot be deflected or absorbed by any shielding system that exists or is close to existing. The secondary particle problem that makes thicker walls counterproductive at the highest particle energies has no engineering solution within reach. The 5% of career dose that Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen accumulate over these 10 days is a real and permanent addition to their lifetime radiation exposure. It is accepted by 4 people who understand exactly what that means, who have read the research, consulted their medical teams, and chosen to proceed not because the risk is trivial, but because they have concluded that the purpose justifies it. The honest calculation is this: 10 days in deep space carries a small but non-zero increase in the lifetime cancer risk of 4 specific people. The data those 4 people generate, from 6 cabin sensors, 4 personal dosimeters, organ-on-a-chip tissue analogs, bone marrow models, and immune biomarker samples, will be used to determine whether the people who follow them to the moon and eventually to Mars can go more safely. That is the trade, stated without softening. Whether the trade is worth making is not a question that physics or biology can answer. It is a question about what humanity values, what exploration costs, and who has the standing to decide when a risk is acceptable. Those questions do not have equations. They have only judgments made by people who have thought carefully about them and chosen to act. If this video helped you understand what those people are flying through and why it matters, consider subscribing so you do not miss what comes next. The Artemis program is only beginning. The radiation science it generates will shape every mission that follows, and every video on this channel will cover it with the same depth and the same honesty you have watched today. What Artemis II has, right now, is 4 people in a spacecraft called Integrity, named by the crew themselves, flying through radiation that is doing what radiation does, with every measurement being recorded, every alarm threshold being monitored, and every data point being fed into the research programs that will determine what comes next for humanity in space. That is what is happening out there. And it is, whatever you think about the risks, an extraordinary thing to witness.